So what I'd like to discuss with you today is what happens when you create a scatter plot and it doesn't look linear, and then you attempt to linearize the data by graphing x first log y, and that doesn't look linear. Then what do we do? So for any data problem, for any problem where you're looking at two variables that are quantitative and you want to compare them, you should always start with a scatter plot of the original data. So we're going to do that. Here it is. It's going to be list 1 versus list 2. And it looks like that's what I have selected here. I've got a scatter plot, list 1, list 2. Press zoom 9 and take a look at it. And sure enough, this data, you might be tempted to think it's straight when you first look at it, but more careful inspection, and what you notice is that a straight line would go through, and while it would look like the R value would be pretty high, you would definitely have a pattern in your residuals. And you kind of see that. Here's the first residual, here's the second, there's something that's 0, negative, maybe 0, maybe something positive. So these residuals would have a pattern where they'd start at positive, go to 0, go negative, and then come back up again to something positive. Okay? So this means that the line is probably not the best fit for the data. Just to make sure, let's go through the steps. Stat, calculate, number 8. So we're doing a linear regression of list 1, comma, list 2. And here we go. We hit enter. We get a very high correlation, almost 1, right? 0.988. R squared, 97.7% of the variation in y is explained by x. This means a line fits onto the data well. Now we're going to see if a line is really the best model by going back to stat plot. And remember, since we just did a regression, there are new residuals. So I'll go to the first stat plot. I'm going to go down to the y list. Okay, and I'm going to do second stat resids. So there we are. Zoom 9, I hit enter. And this is a definite pattern in the residuals. Now, if you tried to follow along, you don't see residuals like this, make sure you actually did a new regression. You have to do a regression with list 1 and list 2 in order to get these residuals. So we know that x versus y is not modeled well using a linear function. So now what we're going to do is we're going to go back to stat edit, and we're going to try the transformation that we worked on in the last video, and that was the one where we did x versus log y. Okay, so that's what we're going to do next. Go to the top list 3, we press log, and then we do second L2, which is the y values. We hit close parenthesis, enter, and here we go. I'm going to go back to stat plot, hit enter here. Let's go down to the y list, and now we're going to put second 3, because we want to graph x versus log y. Press zoom 9, and here we go. Now, if someone looked at this and said, I am not even going to bother trying to fit a line to this because this is nonlinear, I would be fine with that statement. Okay? If you look at the pattern in this set of data now, it definitely looks curved. This is x versus log y. So what does that tell us? It means that we didn't successfully linearize the data. It also means that x versus y is not exponential. We know that because if x versus y is exponential, then x versus log y is linear, right? And that didn't happen here. All right, so this is not the best transformation. And here's where we go and try something new finally. So we're going to go back to stat edit, and here's what's new. So up till now you've been bored. Here things will change. We're going to press log of L1. Log of the x values. Here we go. So now L4 has the log of the x values, and L3 has the log of the y values. So now we're going to do a scatter plot with these numbers. So we do second stat. Okay? And so we're going to go down to the x list and make that L4. There you go. Down, down twice, and press zoom 9. And wow, you couldn't ask for something better than that. That definitely looks linear. You can see it fits a line well. All right, Now we think we've linearized the data. Let's go back to the calculator one more time and do a linear regression on the transformed data. So we go stat, calc, 8. And remember, our x values now are in list 4. So we do second 4, comma. Our y values are in L3. Okay? So remember, these x values are really the log of x. And the y values are really the log of y. Keep going. So we hit enter. And we get a very, very strong correlation. Okay? So this is as close to as good as it gets. All right, so you can see the correlation is basically 1. We're not surprised by that because it's positively associated. Let's write down our line of best fit. So log y hat equals. Now be careful here. This number. All right, so here we are. I circled this value of a because you got to look towards the end here. You see this little e, -4? This really means 3.956 times 10 to the -4 power, which we know from scientific notation means that we have to move the decimal over 4 places. So it's 0.0003956. Okay, plus, and that slope is basically 1.5, because it'll round that way. And here's what's new. I'm going to put the words new here, like you might see on a new flavor of cereal or something, right? Log x. That's what's changing today. Okay? All right, fine. We have a line of best fit for log x versus log y. We know that this is not our goal. Our goal is to transform this back into an equation that has x in it and y hat in it. Okay? So we've done that before, right? We know how to get rid of a log. We do 10 to that power. Okay? Just like we did when we had x versus log y. We're going to do the same thing on the right. 10 to this whole thing as a power, this whole expression. Okay. Things start off looking the same as they used to with the exponential. These cross out, you get y hat. Over here, we recall that rule from a few years ago. So, in our mathematical past, what did we learn? We learned if we had x to the a times x to the b, we had x to the a plus b power. All right? And I've said this, I always kind of like to say it this way. You've been trained to go that direction most of the time, but you've always had the right to go backwards. So the question you should think about is, how can we use this rule backwards, as I put it, to rewrite this side of the equation? So here's what we can do. We can say 10 to the 0.0003956 times 10 to the 1.5 log x. Okay, so this looks a little bit like what we've learned about with exponential functions. If we want to, we can start to write this over. You can say y hat equals, we can get a decimal for that. Okay? 1. I think it's 001. Something like that. About, let's put more decimals. I think it's 1.00091113 maybe. Something like that. Okay, and then over here, I'm going to change this. So just leave that blank for a minute. So I need to remind you something else from your mathematical past. Here's something you learned about a while ago. You learned that you had x to the a to the b power. That was really x to the ab. What about this? Is that true? And the answer is yes, it is, right? So what that means is that we can rewrite this expression using this idea. It'll turn into 10 to the log x to the 1.5. Let's pause for a minute. You might notice that we could have also done the following. Instead of writing the expression that way, we also could have written 10 to the 1.5 to the log x. That kind of looks like this one here. Okay. I made a conscious decision to write this. And if you think about why, you just look at it, you're going to notice something. Let's finish off here. Now what we know is that this coefficient is unaffected by all of this. This just goes along for the ride. But this term now becomes x to the 1.5 power. All right. So there you are. You have an equation with y and x in it. And if you look carefully at it, this is not quite the same kind of equation we had in the last video, is it? Right? Our last equations we had the x variable up in the exponent, and then there was a number. It was a number to the x power. In this case, the x is in the base. And when x is in the base like that, we call this kind of thing a power function. All right. So be prepared to be amazed. So what we're going to do is remember that for a moment. We're going to go to our calculator now. We're going to type that equation in. Here we go. We're going to go back to y equals. We're going to type our numbers. 1.00091113 times x to the 1.5 power. Okay. Now while we're at it, we need to remember that this equation is going to model the original data really well. That's what it's designed to do. So I got to go back to stat plot now. So I'll do second y equals. And I'm going to take this first plot and switch it back to L1 versus L2. So second 1, enter. Second 2, enter. And I'm going to press zoom 9. Oh, wow, that is amazing. It's perfect, okay? Now, before we get too excited, we really should double check our residual graph, right? Just make sure it's randomly scattered. So let's just do that. Go back to stat plot one more time. Hit enter. And go down to the y list. And do second stat, resids. Okay, enter, zoom 9. And we see our residual graph, which looks kind of reasonable. It's a little bit scattered. Some people might argue it's got a little bit of a pattern to it. It certainly doesn't have the distinct pattern that the other one had. Okay? One little thing I should be careful of. Remember when we did this graph, right? When we did this linear regression, we did log x versus log y. So I really should make the x-axis log x. So let's go back to stat plot one more time. This is a small thing. So we'll hit enter here, and then this thing here should be second 4. All right? So we'll hit zoom 9. We'll go down a little bit first. Zoom 9. And the residuals look reasonable. Someone may argue with me, hey, this looks like a pattern except for this point. Someone might say that. All right? But they're certainly better than the previous set of residuals that we had. Previous set of residuals, if you remember, had a very distinct parabolic pattern. So of the three models, linear, exponential, and power, this one's the best. It had the highest correlation with residuals that were the closest to being randomly scattered. Okay?